In this presentation, we will talk about how to design spur gears and their manufacturers. This figure represents the teeth of two gears that rotate about points A and B, respectively. The tooth profiles contact each other at point Q. The instantaneous center for the motion of gear 3 relative to gear 2 lies on the normal to the profile at the contact point. By the Kennedy theory, it also lies on the line joining the centers of rotation of gear 2 and 3 relative to the base. The instant center of the motion of gear 3 relative to gear 2 must be at point I23. It also is known as the pitch point P. So we have the angular velocity omega 2 times the distance AP is equal to the angular velocity omega 3 times the distance VP. Angular velocity omega 2 and omega 3 are in opposite directions. Then we have the velocity ratio R is equal to omega 2 over omega 3. If a constant velocity ratio implies that Vp over AP is constant, that is, P is a fixed point on the line of center between the two gears. Two tooth profiles satisfying constant velocity condition are conjugate. It means these two tooth profiles have a common normal. This slide shows you how to calculate the sliding velocity at the contact point. Sliding velocity Vs is the relative velocity between two coincident points at the contact location Q. It is defined as a difference between rolling velocities of teeth in mesh at point Q. So Vs is equal to omega 2 cross RQ2 minus omega 3 cross RQ3. We know RQ2 equal to RAP plus RPQ, and the vector RQ3 equal to RVP plus RPQ. The velocities of two gears at the pitch point P are the same, so we have omega 2 cross RAP equal to omega 3 cross RVP. For the external gear pair, the angular velocity are in opposite directions. So if omega 2 is positive, omega 3 will be negative. We have the sliding velocity Vs is equal to omega 2 minus omega 3 times the distance PQ. This sliding velocity is proportional to the distance PQ. The velocity is important because the rate of wear of the gear teeth depends on it. Gears can be classified by shape as involute, cycloidal, and trochloidal gears. If a cord is wrapped around a cylinder, as shown in this figure, a point on the cord, as it is unwrapped from the cylinder, trace a curve called an involute. The circle from which the cord is unwrapped is called the base circle. Cycloid tooth form is made up of an epicycloid and a hypocycloid. Truncoid tooth form is generated by a circle. Tooth geometries have many possible shapes. There are two common tooth forms, the involute and the cycloid tooth forms. Cycloid gears are very sensitive to an inaccurate adjustment of the center distance, which then leads to a change in the transmission ratio. For this reason, cycloid gears are hardly found in mechanical engineering, but are only used in special cases, such as in the watch industry for loose type blower. The involute tooth form is the most general gear tooth form. This tooth form is used in almost all cases, except in mechanical watches and clocks. The involute form have several advantages, but two are most important. The first is that it is very easy to manufacture involute gears with simple tooling. The second is that constant velocity ratio is maintained even when the center distance between two gears is changed. The involute profile is developed from a circle called a base circle. The involute is the curve traced by any fixed point on a taut string that is being unwrapped from the base circle as shown in this figure. The involute curve have several important properties. The normal to the involute at any point of the curve is tangent to the base circle. The length of the normal is equal to the corresponding arc length at the base circle. That is, the distance between point BB and B is equal to the arc of BBI. The distance between points CB and C is equal to arc of CBI. The normal distance between the two involute curves is constant, and the length of the normal is equal to the radius of curvature of involute. That is, rho B is equal to the distance between point BB and B. Rho C is equal to the distance between points CB and C. Any two involute profiles are mutually conjugate regardless of the base circle diameters. The path of contact between two involute profiles is rectilinear. Therefore, the pressure angle Y for two involute profiles is constant. The pressure line is called the line of action. Contact takes part along this line. Two involute profiles remain conjugate even when the center distance is changed, but their pressure angle will change. If the center distance increases, the pressure angle increases too. A gear with involute teeth can be generated by a straight-edged rake cutter, so the cutter profile is simple and easy to manufacture. We need to know the basic parameters for the design of spur gears. Most countries use the ISO standard to design gears. The unit of the length in millimeter. Module N represents gear tooth size. You can see this figure. The tooth sizes are from module equal to 1 to 4. Diametral pitch dp is the number of the teeth of the gear per inch of its pitch diameter. By ISO standards, the unit millimeter is decided to express length. However, the unit inch is used in the USA and a few countries. Diameter pitch is also used in these countries. In Taiwan, the ISO unit is applied. For calculation convenience, we normally transform dp to module. Module is equal to 25.4 over dp. Pressure angle alpha is the inclination angle of the gear tooth. An element determines the tooth profile. Typical pressure angles are 14.5 degrees, 20 degrees, 25 degrees. However, 20 degrees gears are most widely used in the industry. The number of the teeth N denotes the number of the gear teeth. We count this gear. The number of teeth of this gear is 10. This slide shows you gear terminology. The pitch circle is the circle centered on the gear axis, passed through the pitch point P. dP is the pitch circle diameter. It is equal to the teeth number N over diametric pitch. The circle pitch PC is curvilinear distance measured on the pitch circle from a point on one tooth to the corresponding point on the next tooth. The circle pitch PC can be computed by the circumference of the pitch circle over teeth number N, and you also can get it by pi over diametric pitch. dB is the base circle diameter. It is equal to dP times cosine of phi. The base pitch PB is the curvilinear distance measured on the base circle from a point on one tooth to the corresponding point on the next tooth. The base pitch PB is the circumference of the base circle over teeth number N and equal to the circle pitch PC times cosine of phi. For other parameters, we have addendum, dedendum, hole depth, face width, and tooth thickness. The addendum circle passes through the tip of the gear teeth. It also is called the tip circle. The addendum is the radial distance from the pitch circle to the addendum circle. The dedendum circle passes through the root of the gear teeth. It also is called the root circle. The dedendum is the radial distance from the pitch circle to the dedendum circle. Hole depth is the sum of the addendum and the dedendum. Face width is the thickness of the gear brake. Tooth thickness is the arc distance, opposite face of a tooth measured along the pitch circle. If two gears are to mesh, it is necessary that their pitches be the same. Since the base pitch, circular pitch, diametric pitch, and module are related. If any one of these pitches measures in the same for both gears, or will be the same, gears cut to standard dimensions are interchangeable, in the sense that any two standard gears can mesh together. For this to be possible, the following conditions are required. The pressure angles must be the same. The diametral pitches of modules must be the same. The gears must have the same addendum and the same dedendum. The tooth thickness must be equal to 1/2 of the circular pitch. This is what permits to open off the shaft gears. However, non-standard gears are also used in many applications for a variety of reasons, some of which is discussed in this chapter. This table shows the standard equations for the 20 degrees and the 25 degrees pressure angles. Their units are inches and degrees. Those are the most commonly used standard gears. A gear system that is not little used is the 14.5 degrees pressure angle. We have the full teeth gear and the stub teeth gear. The stub teeth gear have a shorter tooth height than the full teeth gear. Diametral pitch of module decides gear tooth size. Any diametral pitch is technically possible. However, the standard pitches in common use are 1 to 2 varied by a quarter pitch, 2 to 4 varied by a half pitch, 4 to 10 varied by 1 pitch, 10 to 20 varied by 2 pitch, and 20 to 200 varied by 4 pitch. Based on the equations in the table, the physical size of the gear teeth decreases as the diametral pitch increases. In general, for a given set of pitch diameters, the rod transfer will be smoother and undesirable effects such as noise will be lower if a large number of small teeth is used, rather than a small number of large teeth. This is because more teeth share the load when small teeth are used. An important feature of the gear action is the contact ratio. The contact ratio is average number of the gear teeth in contact. Thus, a contact ratio of 1.2 indicates that one tooth pair is contacting 18% of the time, and the two pairs 20% of the time. If the contact ratio is less than 1, contact will be lost part of the time, and the gear pair will generate noise at a high speed. So, the contact ratio must be greater than 1. A large contact ratio normally means smoother running gears and enhanced load carry capacity and steadiness. This figure shows a pair of mating teeth in two positions, in which they first come in contact and are at the end the point of the losing contact. Between these two positions, the point of contact moves along the line of action. The first and the last contacts are determined by the addendum of the teeth of two gears. Contact is initiated at the point I, which is the intersection of the pressure line with the addendum circle of gear 3. Contact is terminated at point F, which is the intersection of the pressure line with the addendum circle of gear 2. For gear 2, alpha 2 is the angle of approach. It is the angle through which the gear rotates from the time of the first contact between a pair of the teeth, and the time which the contact point reaches the pitch point P. Beta 2 is the angle of recess. It is the angle through which the gear rotates from the time which the contact point is at the pitch point P to the time at which contact is lost. Then theta 2 is equal to alpha 2 plus beta 2. It is the angle of contact of gear 2 when it matches with gear 2. This slide shows you how to compute the contact ratio. Because the distance of the contact point moves along the path of the contact is equal to the curvilinear distance around the base circle. So, we can compute alpha 2 by IP over RB2, beta 2 by PF over RB2, and then theta 2 by IF over RB2. The distance IP from the point of initial contact to the pitch point can be computed from the geometry shown in this figure. Variables RB3, RP3, and RA3 are the base circle radius, the pitch circle radius, and the addendum circle radius of gear 3. Here, Y is pressure angle, and U is the length, IP. For the triangle IPO3, we can use the cosine rule to determine the value of U by these equations. We can also determine the value of B from the triangle FPO2. The distance IF is equal to U plus V. The contact ratio NC can be computed as the ratio of the length of the path of contact to the base pitch. The larger the contact ratio, the smoother the gear operation. Normally, we need to make a contact ratio larger than 1.2. This problem is to determine the length of the path of contact and the contact ratio. In this case, we have two standard gears. The tooth number of gear 2 is 220, and the tooth number of gear 3 is 30. The diametral pitch is 4, and the pressure angle is 20 degrees. We use the formulas listed in Table 11.1 to calculate the circular pitch PC and the base pitch PB. Both gears have the same pitch. We also calculate the tooth pitch radii RP2 and RP3. Then we compute the length of the path of contact lambda. It is equal to 1.185 inches. Then lambda over the base pitch, we can get the contact ratio equal to 1.6. This is a good design because the contact ratio is larger than 1.2.